In this chapter, we talked about the history of atomic theory, the parts of the atom and how they were discovered, and then we talked about how the atoms from element to element are different. We're going to end our time in this chapter by talking a little bit about radioactivity. Here we go. Our study of radioactivity begins with a scientist named Henri Becquerel. One day, Becquerel was developing some photographic film that had been resting in a dark drawer. And the only thing that was present in that dark drawer was some samples of uranium salts. To his surprise, he found that there were images that were created on that film of that uranium reacting. Before this time, he had thought that certain elements like uranium absorbed light from the sun and then emitted it once more. But this showed him and proved to him that it was more than that the uranium on its own was already emitting something. It was called radiation. A few years after that, Marie Curie coined the term radioactivity, referring to this phenomenon of certain elements giving off radiation. As the study continued, it was discovered that these elements that were radioactive were actually undergoing transmutation. That is, converting from one element into a completely different element. And then Ernest Rutherford came along, the same Ernest Rutherford who had the gold foil experiment, and he was able to split the different types of radiation, be able to identify each type. He used a lead-encased radioactive source to emit a beam of radiation through a small hole. After that, it passed through charged plates. One was a positively charged plate, and the other was a negatively charged plate. He found that there were 3 points of impact on the zinc sulfide screen. Zinc sulfide, much like he used in his gold foil experiment. 3 types of radiation were determined from this experiment. One was a negatively charged beta type of radiation, and then there was the alpha type of radiation. Now, Rutherford used that type of radiation in his gold foil experiment. Then a third type was gamma radiation. You may have heard of that from certain comic books. Unfortunately, exposure to gamma radiation doesn't make you green and make you stronger. It'll just hurt you. So from this, it was found that this beta radiation was negatively charged, and the alpha radiation was positively charged. Why? Because this beta radiation would divert toward the positive plate, thus indicating that there was some negative charge to it. And the alpha radiation would divert toward the negative plate, which indicated that it had a positive charge. However, the gamma radiation that was found didn't divert at all and therefore had no charge. So let's discuss each of these types of radioactivity. Here's an example of what happens during alpha emission. For this example, I've used the radium isotope. This is the radium-226 isotope. It has 88 protons because that's what radium has, and an additional 138 neutrons to give us a grand total of 226 for our mass number. The radium is an unstable element, and so radium undergoes radiation. When it does, it will produce an alpha particle. It will emit a part of itself, a part of its own nucleus, in order to try to stabilize a little more. This alpha particle is basically a helium nucleus. It's 2 protons, and that's what helium has, 2 protons, and 2 neutrons. So it's basically the equivalent of a helium-4 isotope. And alpha particles are always that way. That's always what they look like, a helium-4 isotope. We can represent an alpha particle a couple different ways. One is like this, where we show helium, like a helium nucleus, with its atomic number of 2 and a total mass of 4. Or we can simply use the Greek symbol alpha and do the same thing, the 4 and the 2 to the side of the alpha. So this is an alpha particle. It has 2 protons, so it has a charge of 2 positive units, or 2 plus. Since it has 2 neutrons as well, it has a total mass of 4. 2 and 2 give us 4. Here's an equation representation of what's happening. Here's the radium isotope undergoing alpha radiation or alpha decay. And as it does, it releases an alpha particle. So that's one of the products in this. The other is what's left. In this case, once it spits out that alpha particle, what's left is a nucleus that has 86 protons and a total mass of 222. So this is radon-222. So we have radium-226 that undergoes alpha decay to produce radon-222. Notice something about this equation. All the numbers are balanced. On the left side of the equation, we have 226 for our masses. On the right side, 222 and 4 make 226. For the atomic number on the left side, we have 88, and on the right side, 86 and 2, 88. So even in a nuclear equation, the representation of a nuclear reaction, we still obey the law of conservation of mass. So as you write one of these equations, you just make sure that your numbers are matching on both sides, and then you'll know that you're correct. The next type of radiation we're going to talk about is beta radiation or beta decay. To illustrate this, I'm going to use the example of carbon-14. Carbon-14 is a radioactive type of carbon. Carbon-14 has 6 protons, as carbon always does, right? Okay. But it also has 8 neutrons. And the 6 protons and the 8 neutrons give us a total mass of 14. During beta decay, something really interesting happens. To talk about that, I want to talk just for a moment about quarks. You might recall we talked about quarks in a past video. Quarks are what compose protons and neutrons. 2 types of quarks are used to make protons and neutrons, just in different combinations. The 2 types are up quarks and down quarks. In a proton, you have 2 up quarks and 1 down quark. In a neutron, you have 2 down quarks and an up quark. The nature of the quarks even explains why a proton has a +1 charge and a neutron is neutral, 0 charge. It works like this. The proton has 2 up quarks and 1 down quark. Each up quark has a +2/3 charge, and each down quark has a -1/3 charge. So if you have 2 up quarks, you have 2/3 plus 2/3. That's 4/3. But then you have a down quark in the proton, and that's -1/3. So 4/3 minus 1/3 gives you 3/3. Positive 3/3 or +1. Get it? So that's how a proton has a +1 charge. The neutron has 1 up quark +2/3 and 2 down quarks -1/3 -1/3. 2/3 -1/3 -1/3 is, right, 0. That's how a neutron is completely neutral, 0 charge. You get it? So in beta decay, one of the down quarks in this neutron changes sides and becomes an up quark. Isn't that wild? So now you've gone from having 6 protons to 7 protons. And in doing so, you've changed the identity of the element. In the process, as this neutron becomes a proton, it spits out a very, very high velocity electron. We call that a beta particle. And a beta particle is just basically a fast-moving electron. So when you hear beta particle, just think electron. It has a charge of 1 negative unit, -1, and the mass is 1/1840th of an AMU. Extremely small, so we basically just say 0. To signify a beta particle, we use the Greek letter beta. And we have a mass of 0. It's a little hard to write 1/1840th, so we just say 0. But you'll notice we have a -1 here. Let me show you why. Remember that the result of an element undergoing beta decay is that it increases its atomic number by 1. In the case of carbon-14, it goes from 6 protons to 7 protons. And since 7 protons can't be carbon, that must be nitrogen. So carbon-14 changes to nitrogen-14 and spits out a beta particle in the process. So in our equation that represents this reaction, we need to make sure that the numbers agree. The law of conservation of mass. The mass on the left side is 14. The mass on the right side, 14 plus 0, 14. The atomic number on the left side, 6. And this is why we have the -1. So that the atomic numbers on the right side will also equal 6. So in a beta decay, you'll always show the beta particle as having a 0 mass and an atomic number of -1. And that will work out when we write our equation. Make sense? So here's the takeaway for beta radiation. During the decay process, one of the neutrons in that radioactive isotope changes to a proton. So you increase the atomic number by 1. And in the process, a very fast moving electron is emitted from the nucleus. That's beta decay. For our third type of common radiation, this is gamma emission or gamma decay. Gamma radiation is extremely high energy, very big energy. It's on the highest end of our electromagnetic spectrum. And again, unfortunately, you don't become green, you don't get strong by being hit with gamma radiation. It just destroys your body, pretty much. Now, gamma decay actually accompanies alpha decay or beta decay, and it's responsible for the energy that comes from those reactions. Here's a situation where we have uranium. This is uranium-238. Uranium-238 has 92 protons because that's what uranium has. It also has 146 neutrons in its nucleus to give it a total mass number of 238. When uranium undergoes alpha decay, you see that? There's that helium nucleus, or you can also represent it this way, with its total mass of 4 and its 2 protons. When it undergoes alpha decay, it produces thorium, thorium-234. Thorium has 90 protons, and it has a total mass number of 234. So notice that the numbers add up, don't they? 238 on this side, 238 on this side, 92 on this side, 92 on this side. And you'll also notice this symbol on the end. This is the symbol we use to represent gamma radiation. This is the Greek letter gamma. It's a lowercase gamma. And you'll notice I have zeros. A 0 here, a 0 here. That's because gamma has no charge and no mass. Again, it's just all energy. Because it has no charge, it's not deflected. Remember our diagram from before? The gamma radiation is not deflected by a positive or negative charge. It just goes straight as an arrow. Since gamma rays are massless, they are not responsible for the transmutation, the changing of an element to something else. They are simply the energy that comes from such a reaction. If you're wondering about the penetrating power of alpha, beta, and gamma, it's about like this. For alpha radiation, it's fairly easy to stop. You could probably have a good solid piece of cardboard and do that. Beta, you would need a little bit more, perhaps even some really thick clothing to take care of that. But gamma, now we're talking about lead lining, reinforced concrete, that kind of thing. Gamma has extremely high penetrating power, and that's why it's so dangerous. If you're wondering why some of these elements are radioactive, it has to do with their instability. And that has to do with the ratio of protons and neutrons. Elements that have too few neutrons are unstable, and elements that have too many neutrons are unstable. So the process of radiation involves that atom attempting to stabilize itself by releasing part of its nucleus. And some elements go through several decay processes before they get to a level in which they are stable. But that's the reason why they do it, because their nucleus is unstable. Once they release part of it and give themselves a little more room to breathe, they become a little bit more stable. And by the way, this is just an overview of nuclear chemistry. We'll go into much greater detail of nuclear chemistry in chapter 24. So that's all the time we have for today. Today we talked about the different types of radiation. We talked about alpha radiation, beta radiation, and gamma radiation. We also talked about just a little bit of the history behind radioactivity. As always, I hope it's been helpful to you. In the next chapter, we will start discussing the elusive electron and some of the mysteries surrounding it. I think you're going to find it interesting. So, until the next time, God bless.